In the final slides, I want to make our description of diffraction more exact and more general, such that it also applies to positions closer to the diffracting object. And the key word in that more general description is the field propagator. So the idea is, as usual, that we have illumination, typically plane wave illumination. We create a series of secondary Huygens sources inside the diffracting object, and these sources, they emit towards what we previously called the far field, where we considered the diffraction as a function of angle, but which in this more general description is the field at a certain transverse displacement y prime at the distance L away from the scheme, which is not necessarily far away, right? If you were far away, your theta has the flavor of y prime over L, at least if you are paraxial in the simple case, and otherwise you have to worry about sines or tangents or things like that. But so this is the general form. The idea is you have these Huygens sources. You have to integrate over the Huygens sources, and each of these sources propagate in a certain way from the position of the source to the position of the detector. And this propagator comprises two terms, two factors. One is a phase factor, which basically accounts for the phase acquired during propagation. So this combination k times L, where L is the length, the path length from the source to the detector. And it also contains a term related to the dilution of the field. It spreads out over a spherical shell. And if you look at that other factor, you notice that in the two-dimensional approximation, this prefactor is actually 1 over square root L. More precisely, 1 over the square root of I times L times lambda. And only in the 2D case is it like 1 over L with an additional factor I and L. Well, we won't worry about these prefactors. What we worry about is this phase factor, which even if the path length changes by a wavelength lambda, the phase factor can change completely from constructive to destructive, etc. Right? So it's all about this path length, and from Pythagoras you can easily write this path length, which depends on the transverse position of the emitter and the transverse position of the detector. You can write it as the square root of L squared plus y minus y prime squared transverse displacement, difference in transverse displacement. And you can also write this by using a Taylor expansion. So you take out this L squared term, and if you then Taylor expand, you can approximate it as L plus L minus L prime over 2L. Right. So this is the general form. It's all about path length differences. And when we previously considered the far field, we basically only worried about this y prime, or actually y prime multiplied by y, but we never worried about y itself. That changes if you're closer. If you get closer to the source, you also have to worry about this y term, as you'll see in the next slide. This slide shows how the diffraction pattern behind the slit of size d changes with increasing distance. Previously, we considered the diffraction pattern far away. And if you're far away, you only have to worry about the output field as a function of angle. So if you're further away, the pattern becomes bigger, but as a function of angle, it basically looks the same. There's only scaling, right? And this far field diffraction you call Fraunhofer diffraction, which already is here. Now, if you get closer to the slit, you notice that the pattern, of course, shrinks, like you see here, but then if you get closer, you get all these funny interference fringes. These intriguing interference fringes, which you call Fresnel fringes, because this region of diffraction close to the slit is called the Fresnel diffraction. Right? And you see that if you're really close, the field pattern sort of starts resembling the pattern that you would naively think, which has uniform intensity inside the slit and zero intensity outside the slit, right? But there's still some weird fringes. Now, if you think about the transition region, where does this Fresnel regime ends and where does the Fraunhofer regime start, then it's an easy way to figure it out. I mean, if you look at the typical size of the pattern in the Fresnel regime, yeah, you're limited. You're close by the slit, so your pattern will have a width comparable to the size of the slit. On the other hand, if you're far away, in the Fraunhofer regime, you typically talk about the diffraction as a function of angle, and we already saw that the diffraction angle is given by this most important equation in optics, lambda over d. So at the distance L, the size of the pattern, the actual size, is L times theta, so is L times lambda over d. And so this crossover is where this diffraction expression is equal to the expression that you would naively think. So the crossover is at a distance L equal to d squared over lambda. So Fraunhofer regime, to be in the Fraunhofer regime, you have to be at a distance bigger than d squared over lambda. This slide shows two cute photos of diffraction in the Fresnel regime. So diffraction patterns observed close to the object. On the left side, you see the diffraction pattern behind the screw. You recognize the screw here, but you also recognize that there are some weird interference fringes in the observed Fresnel pattern. These are Fresnel fringes. On the left side, on the right side, sorry, you see the diffraction pattern behind an edge in the screen. So you have a screen that blocks the light, and so you would naively expect no light here at the point where the screen blocks and uniform intensity here at the point where the screen transmits, where there is no screen. What you actually observe is you see some fringes which basically look like this. So, strangely enough, you see that by blocking part of the light with the screen, very close to the screen, you actually increase the intensity by putting a blocking object there. The idea that you can get more light by partial blockage of the beam is even more extreme in what's called a Fresnel lens. So Fresnel lens is a plate with rings that either pass the light, the white rings, or block the light, the black rings. And this Fresnel lens, if you illuminate it from the back, is a plane wave, And look on axis at the intensity at the point at a certain distance r0 from that Fresnel lens. What you can find is that the intensity at this point can be much, much bigger than the incident intensity which you would observe in the absence of this screen. So by blocking part of the light, here with the screen, you can boost the intensity at a specific point. This screen with the rings, this Fresnel lens, acts somewhat like a lens, hence the word Fresnel lens. So how does it do the job? Well, for that, you can look at the expression which relates the input field, the field at the screen, which you have to integrate over all positions in the screen, and in particular only over the regions that transmit, so only over these circular white regions. And then each of these contributions acquires a phase factor of this form, which is related to the propagation length, the distance from the source to the point at which we measured the field. And this length increases, of course, if you're further away of axis. So you start with a certain reference length, r0, but then at a certain distance away of axis, this length is lambda over 2 bigger, right? So contributions from that part are then 180 degrees out of phase with contributions from the center. If you would draw phasors, you would say, hey, this, if I call this the phasor of the central contribution from the center, then if I go a little bit off axis, I get contributions from points off axis which are related to longer paths, so to acquire phase change due to this longer propagation. And then these contributions at some point are I'm so far that the contributions are 180 degrees out of phase. And if I then look at contributions further down the line, they're even more than 180 degrees out of phase, and they will interfere destructively with the light I already have. Right? So the idea is that if you would integrate over all these contributions, you would have a whole series of phasors which would almost average out, but still produce a field equal to the input field. But if you block those phasor contributions here in this lower complex plane and only leave the ones in the top complex plane, then they mainly interfere constructively, and you can have a much, much bigger field. Right? And that's expressed by this idea that if you think about the field contributions from consecutive parts in a plate, then you can define what's called Fresnel zones. So regions for which the path length difference between the path from this source to the detector relative to the central path, this path length difference multiplied by k produces m times pi phase difference, or m minus 1 times pi